There is no magnet inside the Earth. There can't be one. Iron only holds on to magnetism while it stays cool, and the limit is sharp. Heat it past about 770 degrees, and iron forgets, not slowly, not partly, but completely. The core is thousands of degrees past that. So whatever your compass needle is answering to, it isn't stored down there. It's being manufactured continuously, right now. And you can calculate what happens if the manufacturing stops. With the metal held still in the equations, the field bleeds away by simple diffusion in something like 30,000 years. That's the entire reserve. Every ship, every aircraft, every drill bit, every little arrow on a phone screen rests on the assumption that a machine nobody has ever laid eyes on keeps turning over smoothly and drifts slowly enough that we can stay ahead of it. If that's your kind of unsettling, subscribe and leave a like. And tell me in the comments which city you're watching from and what your clock says right now. The field standing over you at this moment measurably isn't the one standing over me, and I'd like to know where you all are inside it. Start with the forgetting, because it kills the picture most of us were handed at school. The bar magnet buried in the middle of the globe, north end up, sitting there since the beginning. Nothing that deep can be a permanent magnet. The magnetism of iron comes from countless atoms holding the same alignment, and heat is precisely the thing that shakes them out of it. Past a certain temperature, the ordering simply fails, and it fails everywhere below a shallow rind of crust. The first hard evidence that the field is something happening rather than something present come out of London, and it took 54 years for anyone to accept it. In 1580, a navigator measured how far the compass needle sat off true north on the Thames at Limehouse, roughly 11 degrees to the east. In 1622, the man who held the astronomy chair at Gresham College repeated the measurement and got a markedly smaller number, which was written off as carelessness by the first man. 11 years after that, his successor, Henry Gellibrand, went out and measured it himself, 4 degrees east. He finally admitted what the numbers had been saying for half a century. The needle had swung most of the way across that gap within a single lifetime. He sat on it for more than a year before publishing, and the hesitation is the interesting part. A compass that changed its mind wasn't wrong in the sense of being improbable. It was wrong in the sense of being impossible. The Earth was a magnet, and magnets don't wander. Direction we've tracked ever since through ship's logs and harbor surveys and later permanent observatories. Absolute strength is a younger record. The first real network of magnetic stations went up in the 1840s, and everything we can say about how strong the field actually is begins there. The two records agree on one thing: nothing about this holds still. So, back to the arithmetic. A field with no generator behind it decays, and this one has been here for at least 3.5 billion years. Something is remaking it faster than it dies, without a break, for most of the age of the planet. That something sits 3,000 kilometers beneath your feet. Nobody has ever seen it. Nobody ever will. We know it's liquid without going anywhere near it, and the proof arrives every time a large earthquake goes off. Quakes send two kinds of wave down through the planet. One is a compression, a push, and a release, and it travels through anything: rock, water, air. The other is a shear, a sideways flick, like the wave you send along a rope, and it needs a material that resists being twisted. Liquids don't resist. Seismometers spread across the world catch the arrivals from a big quake, and there's a broad band on the far side of the planet where the shear waves never show up at all. The edge of that silence marks a boundary at a depth of about 2,900 kilometers. Below it, nothing holds its shape. In 1936, a Danish seismologist working through records of New Zealand earthquakes found faint compression arrivals inside a zone where the models said there should be nothing. The only way to put them there was to bounce them off something hard, deep inside the liquid. There's a solid ball at the center of the melt, and it's still growing. That arrangement is the whole engine. The outer core is liquid iron with some nickel and a scattering of lighter elements stirred through it, and it has been slowly cooling since the planet formed. As it cools, iron freezes onto the solid ball at the middle. Freezing does two useful things at once. It dumps latent heat into the fluid just above the boundary, and the light elements don't fit into the growing crystal, so sulfur, oxygen, and silicon stay behind in the melt. At the base of the liquid layer, you end up with fluid that's both hotter and lighter than what sits above it, and it rises. Cold, dense fluid sinks to take its place. That's convection, running in metal, across more than 2,000 kilometers of depth, for 1 billion years and counting. The rotation is what turns it into a compass instead of a mess. Earth turns once a day, and in a spinning frame, every column of rising fluid gets pushed sideways as it climbs. The flow organizes itself into long columns lined up with the spin axis, because that's the one direction the rotation doesn't fight. Moving metal drags magnetic field lines along with it, stretches them, rubs them around, and feeds the result back into the flow that made it. That loop settles into a field which is roughly a dipole and roughly aligned with the axis you spin on. The alignment isn't a coincidence, and it isn't exact either. Magnetic north has never once been the North Pole. The strength is the strange part. The field you're standing in is feeble, far too weak to hold a paperclip to a refrigerator door. The only reason you ever notice it is that a compass needle is free to turn and has nothing else to do all day. Down in the core, it's a different object entirely, perhaps 50 times stronger than anything that reaches your hands. That figure didn't come from an instrument. The moon and the sun raise tides in the liquid core the way they raise them in the ocean. Metal sloshing across magnetic field lines generates electric currents, and currents bleed energy as heat, which damps the sloshing. The damping shows up as a tiny irregularity in the way Earth's axis nods over the years. Working backwards from that nod gives you the field strength in a place no probe will ever reach. And that machine is the reason there's air above you to breathe. The sun throws off a continuous wind of charged particles, and charged particles crossing a magnetic field get bent. The field stands that wind off tens of thousands of kilometers out, and everything underneath rides in the shelter of it. Without the field, you'd be standing in the wind. All of that is inference. Careful, cross-checked, agreed on, and still inference, because nobody has ever sampled the core, and nobody is going to. There's exactly one place where the field wrote down what it actually did, in a form you can pick up and carry. Stone. Watch a lava flow cool. While it's molten and glowing, the magnetic minerals inside it are free. The field around them is far too weak to line them up while heat is throwing them about. As the flow drops through a few hundred degrees, each grain crosses its own forgetting point, going the other way, and locks. Whatever direction the field happened to point that afternoon is now built into the rock, and short of melting it again, nothing will change it. A basalt flow is a note written in a single afternoon and never revised. In 1906, a physicist named Bernard Brunis, who ran the observatory on the Puy de Dôme in central France, measured a flow in the Cantal. Its magnetization pointed the wrong way, roughly opposite to the field he could measure standing on top of it. On its own, that proves nothing. Rocks do odd things. What made it serious was the clay underneath. The lava had come down on sediment and baked it. The baked clay had cooled through its own locking temperature in the same hours, and the clay pointed the wrong way too. Two different materials, two different chemistries, one shared moment of cooling. The same impossible answer. In 1929, Motonori Matuyama worked through volcanic rocks across Japan, Korea, and northeast China, found both kinds, normal and reversed, and noticed something nobody else had. The reversed ones were consistently the older ones, everywhere he looked. That turns a curiosity into a clock. Then it fell apart, and stayed apart for 20 years. In 1951, Louis Néel published a mechanism by which a mineral could take on a magnetization pointing against the field it cooled in. Two magnetic phases inside one crystal, coupled so that the stronger phase wins and drags the total the other way. Within a year, a dacite from Mount Haruna in Japan was found doing exactly that in the laboratory, on demand, repeatably. So now every reversed rock on Earth had an innocent explanation sitting next to it. Maybe the field had flipped. Maybe the rocks were doing it to themselves. Lava is the cleanest recorder, though it isn't the only one. Sediment settling on a lake floor keeps a record too, more ruggedly. Magnetic grains drifting down through water get nudged into alignment before the mud closes around them. And some of those grains are crystals grown inside living bacteria. Fired clay records it as well, and so does a kiln floor and a hearth. What closed the argument wasn't a cleverer magnetic measurement. It was a clock borrowed from a completely different branch of physics. Potassium in a lava flow decays into argon at a known rate, and the argon only starts accumulating once the rock has solidified, so you can date a flow without touching its magnetism at all.
Through the early 60s, two groups did this in parallel, one on flows in the Sierra Nevada, one across the Hawaiian Islands, and then compared. Rocks of the same age carried the same polarity, in California and in the middle of the Pacific, in different lavas with different mineralogy. A crystal scale quirk can flip one rock. It cannot arrange for flows on opposite sides of an ocean to flip at the same moment and stay flipped for the same stretch of time. The reversals were real, and by the mid-60s, there was a rough calendar of them. And then the record answered a question nobody had thought to ask it. Ships had been towing magnetometers behind them since the war, mapping the ocean floor, and the maps kept coming back striped. Long parallel bands with the field read slightly high, alternating with bands where it read slightly low, running for hundreds of kilometers. Nobody could account for the pattern. In 1966, a profile taken across the Pacific-Antarctic Ridge by a converted Navy ship was spread out on a desk and read properly for the first time. The stripes on one side of the ridge were a mirror image of the stripes on the other, band for band, width for width, out to 500 kilometers in both directions. There's only one way to get that. New crust is being made along the ridge. It locks in whatever polarity the field has as it cools, and it's carried away from the axis in both directions at once. The stripes are the reversal calendar, printed twice, running outward. Rocks that had been an embarrassment for half a century turned into the proof that the continents move. So the machine works and the record is real. Which leaves a question that sounds like bookkeeping and isn't. Where does the energy come from? None of this is free. Keeping that much liquid metal turning over and driving electric currents through it against its own resistance costs power continuously. Power on the scale of terawatts, with no pause, for billions of years. The standard answer is the freezing at the inner core, the ball growing, shedding heat and light elements, buoyancy driving the churn above it. There's a problem with the timing. The inner core is young. Estimates of when it began to freeze run from 500 million years ago to more than 2 billion, depending on the assumptions you feed in. And that's a genuinely open range rather than a rounding error. The field is older than any version of it. Magnetized crystals put a working dynamo at 3.5 billion years. For most of this planet's history, there was no inner core to freeze. Whatever ran the machine back then had to be plain cooling, hot fluid rising because it was hot, and nothing else. That was fine until somebody measured the iron. To know how much of the core's heat escapes by convection, you first have to know how much escapes by simple conduction, seeping straight up the temperature gradient and doing no useful work at all. That quantity is the thermal conductivity of iron at core conditions, 1 million atmospheres, temperatures rivaling the surface of the sun. And for decades, it had been a theoretical estimate nobody could check. Starting around 2012, groups began pinning down real values, both by first principles calculation and by squeezing specks of iron between diamond tips and heating them with lasers. The answer came back 2 to 3 times higher than the old figure. That sounds like a technical footnote. It's a demolition. If iron conducts heat that well, then warmth leaks out of the core without stirring anything, and the fluid can sit perfectly still while it cools. Running the numbers backwards through Earth's history, the dynamo starves. It shuts down long before the inner core exists, and once it's down, there's nothing to restart it.
The field should not have survived. It did. The mismatch has a name now, and it's been open since 2013. There are candidate fixes. Perhaps there's more radioactive potassium down there than anyone assumed, heating the core from within. Maybe the mantle above was hauling heat away faster in the early Earth than the models allow, where the light elements separate out in ways that drive flow with no temperature difference involved at all. Any of those could work. The people who do this for a living haven't settled which, and there's evidence that the machine really did come close to quitting. In a 565-million-year-old intrusion in Quebec, the field is recorded inside single crystals of feldspar and pyroxene, in microscopic magnetic inclusions sealed there when the crystals grew. The most sheltered recorders anyone has found, immune to most of the things that spoil a rock's memory. Averaged across that interval, the field they hold is about 10 times weaker than the one outside your window. It's the feeblest long-term field in the geological record. The directions are scattered wildly, and the polarity is flipping many times more often than it does today. That combination is the signature of a dynamo that can barely hold a shape. Then it comes back. Rocks from a few tens of millions of years later record the strength climbing several times over. The most cited reading of that sequence is that this is the moment the inner core began to freeze, and a starving dynamo abruptly acquired a new power supply. That's a reading rather than a settled result. The data are thin and hard-won, and the alternatives aren't dead, but it matches what the thermal models predict, and nobody has produced a better account of why the weakest field in the record is followed immediately by a strong one. Which leaves us here. The machine we've been admiring, with its rotating columns and its dipole obligingly lined up with the spin axis, doesn't have the fuel to explain its own history. And there's a stretch of the record where it very nearly went out. Mars has crustal rocks that were magnetized once and never again. Whatever ran that planet's dynamo stopped, and stayed stopped. The field you live under isn't a fixed property of the Earth. It's the output of a process, and the record says the process has already come within sight of stopping once. So we watch it. Since 2013, 3 satellites have been flying in formation in polar orbit for exactly this purpose. 2 of them side by side at lower altitude, 1 higher up. Between them, they now hold the longest unbroken magnetic record ever taken from space. They can't see the core. They measure the field itself, and then the far more useful quantity underneath it, the rate at which that field is changing. The mantle in between is a poor electrical conductor, which turns out to be a gift because it lets the core's signal through instead of smearing it. Fine detail gets blurred on the way up, so the small stuff is lost, but the large-scale flow patterns arrive intact. Then you invert. You take the changing pattern at the top of the atmosphere, and you solve for the motion at the top of the core that would produce it. What comes out is a map of a moving liquid nobody will ever photograph. The first thing that map showed was unexpected. Under Alaska and Siberia, there are bright patches in the field, places where the flux comes through strongly, and those patches make changes easy to see. Tracking them turns up a band of liquid iron circling the pole at more than 40 kilometers a year. Ordinary flow down there is perhaps a third of that. Compared with the tectonic plates, which move at the speed a fingernail grows, it's ludicrous, hundreds of thousands of times faster. It's confined to a band for a reason. The solid inner core casts a kind of cylinder up through the liquid, aligned with the spin axis, and fluid behaves differently inside that cylinder than outside it. Along the boundary, metal converging from both sides has nowhere left to go except sideways, and it accelerates along the line. The jet is what a collision looks like when the colliding material can only escape in one direction. It's also getting faster. The jerks are the reason nobody will tell you where this field will be in 20 years. Every few years, the field's acceleration changes abruptly. Not its value, not its rate of change, but the rate at which the rate is changing. And it does this worldwide, within months, with no warning at all.
The leading account is that waves traveling inside the core, far faster than the sluggish convection carrying them, arrive at the top of the core and focus their energy there. Slow motion in the metal, fast messengers running ahead of it. 50 years after they were first noticed, the argument about where jerks come from is still live. In 1995, a supercomputer ran the whole thing from first principles. A year of computing time bought 40,000 simulated years of core convection, and the simulated field came out looking like the real one, dominated by a dipole, drifting slowly westward at the surface, roughly the right strength. Near the end of the run, it reversed. Nobody had put that in, and the modelers said afterward they hadn't expected it. It just came out of the equations, the way it apparently comes out of the metal. The real thing did it long enough ago to be abstract, and recently enough to argue about in decades. That boundary is the one the whole polarity scale hangs from. Below it, reversed, above it, the world you live in. For decades it was quoted at 780,000 years ago. A synthesis published in 2019 pulled together lava flows, deep-sea sediment cores, and ice records with careful, independent dating, and moved it to about 773,000. Even the anchor date got revised. The fight is over how long it took, and the two answers aren't close. In the central Apennines, in a mountain basin near Sulmona, there's an old lake bed exposed at the surface, and it's an unusually good recorder. The mud is fine and even, the deposition rate is steady, and it's threaded with layers of volcanic ash from eruptions nearby, each of which can be dated directly by argon. So you get a section where you know how many years each centimeter of sediment took to lay down. Sampling up through it, reading the direction the grains are pointing, you can watch the field turn over. That section shows a direction swinging all the way over at a rate of under 2 degrees a year, with no intermediate stopping points recorded anywhere along the way. The whole final flip lands inside a single human lifetime. Call it a century, the sort of change that a person born at the start of it could have noticed with the instruments of the 1600s. Against that stands the other approach. Every usable record of the same reversal from around the world stacked together, then asked when the global field left its normal state and when it settled into the new one. Those compilations give 20 to 30,000 years. Both numbers come out of careful work, and neither side has conceded. The most popular way of holding them together is that the Italian record is real but local. A violent regional lurch inside a long, rugged global transition, with the field going incoherent for millennia, while one patch of the planet swings through in a century. Other groups have challenged the Italian section on technical grounds, arguing that some layers were remagnetized after the fact. It isn't resolved. The strangest part of that record is what carries it. The magnetism in that Italian mud is almost entirely biological. Across the intervals spanning the reversal, the sediment is nearly pure biogenic carbonate, and the magnetic mineral in it was manufactured by bacteria. Certain microbes build chains of magnetite crystals inside their own cells, each crystal grown to a size where it holds a single stable magnetic direction, the chain assembled along a protein scaffold. The chain aligns the whole cell with the field lines, which lets the bacterium swim along a straight track through sediment instead of wandering. They were described in the mid-70s, and once anyone went looking, the crystals turned up throughout the geological record. So when those cells die, the chains settle out and lie down in the mud, pointing where the field pointed. Stack enough of them and you get a record. The most precise account we have of the last time this planet's magnetic field turned over was written by bacteria going about their business. A century of that transition takes up a few centimeters of gray lake mud you could hold between two fingers. 700,000 years is a number, though. Nothing that far back has any grip. The near miss does. About 41,000 years ago, the field very nearly went. It's named for a set of lava flows near Clermont-Ferrand in central France, where it was first spotted in the 1960s. And for 2 decades afterward, it was suspected of being a mineral artifact until direct strength measurements settled it. The dipole fell to about 5% of what it is now,
the poles crossed over, the field held reversed for a few centuries, and then it came back to where it had been. The transition each way took a couple of centuries. Even at its strongest, during the whole episode, it was running far below anything in human historical memory. The reason we can be confident about that is that it was recorded twice by two systems with nothing in common. Cosmic rays hitting nitrogen and oxygen high in the atmosphere break them apart and make beryllium-10, an isotope that doesn't otherwise exist here in any quantity. The weaker the magnetic field, the more cosmic rays get through, the more beryllium-10 gets made.
It attaches to aerosols, falls out in snow, and gets buried. In the Greenland and Antarctic ice, counted layer by layer, the production rate roughly doubles right where the lava flows say the field collapsed. Rock chemistry and ice chemistry, sharing no assumptions, no instruments, and no physics beyond the field itself, pointing at the same few centuries. Reconstructions of what the magnetosphere looked like during those centuries have been run recently, and the result is worth sitting with. As the dipole faded, the field stopped being a simple two-pole arrangement and went lumpy. Several poles, a tangled structure, closer to what the outer planets carry than to anything Earth has now. The ring of sky where charged particles pour in, which today brushes northern Norway and the Canadian Arctic, detached from the pole and slid south. Spain glowed. Northern Egypt glowed. If you'd been standing in southern Europe on the right night, the sky over your head would have been doing something no human being has seen from that latitude since. And it would have kept doing it, on and off, for generations. People lived through all of it. Whether it did anything to them is a separate question, and a contested one. And the thing steering all of it is meanwhile moving faster than at any point in the written record. The magnetic North Pole is the spot where the field points straight down, where a needle, free to swing in all three dimensions, would stand vertical. A British expedition planted a flag on it in the Canadian Arctic in 1831. Reconstructions built from 4 centuries of ships' compass readings show it wandering around northern Canada that whole time, at 10 kilometers a year or less, which is slow enough that a good chart stayed good for a working lifetime. From the mid-90s, it took off. The drift climbed steadily until it was covering 55 kilometers a year. In 2017, the pole crossed the international dateline into the eastern hemisphere, passing closer to the geographic pole than it had come in recorded history, and kept going toward Siberia. That created a practical problem, and the shape of the problem tells you how much of modern life is quietly bolted to this. There's a global model of the field, rebuilt every 5 years, that converts what a magnetometer reads into an actual bearing. Aviation runs on it, shipping runs on it, so do submarines, parachute drops, antenna pointing, and a long tail of military systems. And so does the compass app on your phone. In 2019, the version then in service failed its annual accuracy check well before its expiry date. An emergency replacement had to be issued a year ahead of schedule, and the release itself was delayed by weeks because the agency responsible was shut down at the time. Airlines reloaded navigation software across entire fleets. Far enough north, the model stops helping at all. Near either pole, the field is pointing almost straight down, so there's barely any horizontal component left for a needle to align with, and the compass has nothing to work with. Aviation charts mark those regions as blackout zones. Inside them, magnetic navigation is simply unavailable, and the boundaries of the zones move as the pole does. The cause turned up in the satellite data. 2 large lobes of inward flux sit on the core mental boundary, one under Canada, one under Siberia, and between them they largely decide where the pole sits at the surface. They've been tugging against each other for centuries, and Canada has always won. Then, sometime between 1970 and 1999, the flow in the core changed and stretched the Canadian lobe out east to west, splitting it into 2 joined halves. A stretched lobe has a weaker signature at the surface. Canada's grip loosened, Siberia's held, and the pole started walking toward the winner. That was the explanation. It worked. and everyone extrapolated from it. The model said the pole would continue on the same heading for another several hundred kilometers over the coming decade. Then it braked. Over the past 5 years, the drift has dropped from around 50 kilometers a year to about 35, the largest deceleration ever recorded in a record that goes back 400 years. Nobody has an accepted explanation for it. The behavior of magnetic north over the past 3 decades, sprint and stop together, is something no one has observed before, and every projection built on the way it was moving is now worth nothing. 2,500 kilometers south of all that, something slower and more consequential is going on. On a map of South America and the South Atlantic, the total field strength over that region reads far lower than anywhere else at that latitude. It isn't a hole punched through a shield. Directly underneath, at the top of the core, there are patches where the flux runs the wrong way, where the field lines, instead of leaving the core and heading out into space, turn around and go back down into it. Locally, that cancels a piece of the dipole. The overall field is the sum of everything the core is doing, and here the sum comes out small. The consequence sits overhead. Charged particles from the sun get caught in belts around the planet, held there by the field, normally standing off at a comfortable distance. Over the South Atlantic, the weakness lets the inner belt sag, and its lower edge comes down to a few hundred kilometers, which is exactly where things we've launched are flying. The satellite trio has now watched this region for more than a decade, and the numbers aren't reassuring. Since 2014, the weak area has grown by roughly half the area of continental Europe. It's drifting northwest. And since about 2020, it's been coming apart into 2 separate minima, one over South America and one further east, with a ridge of slightly stronger field between them. The eastern half is the one moving. Southwest of Africa, the field has been dropping noticeably faster than on the American side, and one of those inward-pointing patches has been tracked crawling westward across the continent, dragging the weakness with it. The bigger question is why it's there at all, and the answer appears to start above the core. Underneath southern Africa, at that same boundary, seismic waves slow abruptly as they pass through a vast region of the lowermost mantle. It's thousands of kilometers across, hundreds of kilometers tall, chemically different from the mantle around it, and it has been sitting in roughly that spot for tens of millions of years at minimum. It changes how quickly heat can leave the core underneath it. Change the heat flow out of one patch of the core, and you change how the metal beneath it convects. And the leading proposal is that this is what decides where the core sheds reversed flux in the first place. The mantle deciding where the core misbehaves. Nobody has shown that it has to be so, and the alternative is that the anomaly is a wandering feature that happens to be there now. The way to test a proposal like that is to ask whether it has happened before in the same place, and there's an answer. Iron Age farming communities in the Limpopo Valley, in the country where Zimbabwe, Botswana, and South Africa now meet, responded to drought by burning down grain bins and hut floors as a ritual of cleansing. The clay cooled afterward and recorded the field exactly the way baked clay does. Those floors can still be found intact, each one a tiny observatory frozen at the moment its fire went out. And sampling them across dozens of sites yields a regional record running from around the 5th century to the 16th. The record shows the field in southern Africa dropping around 1300 at a rate as steep as the one measured there today, down to lower values than the present. Then it climbed back. There's a second, earlier interval of rapid change in the 6th and 7th centuries. Whatever is happening under the South Atlantic now, the same region has done it at least twice before, without the planet's field going anywhere. So much for the geology. Up here, it's already an operating expense. The most productive telescope ever built crosses the anomaly 10 times a day, and for something close to a sixth of its working life, it can't take data at all. The background from charged particles swarms the detectors, and observations are simply not scheduled through the passage. It isn't only a matter of noise. A single high-energy proton through the wrong transistor flips a bit,
and the flipped bit in a memory cell holding executing code can send the spacecraft somewhere unrecoverable. Operators across low Earth orbit power down non-essential systems before entry as standard practice, and the ones that stay on log resets and lost data every month. Here's what that looks like from inside a human body. Astronauts in a darkened module, eyes shut, dark adapted, see flashes, points, streaks, occasionally little bursts. They're not imagining it. Charged particles are passing through the eyeball and being registered directly by the retina, which is working for those few milliseconds as a particle detector. Over most of an orbit, the rate is 1 or 2 every 10 minutes. Crossing the anomaly, it climbs to several a minute. The crew members who sleep nearest the outer wall of the station see more of them than the ones bunked deeper inside. None of that is a storm, and the distinction matters. The anomaly is a standing weakness in the field, always there, changing over decades. Storms are weather arriving from the sun, and what they do to the ground is a different mechanism entirely. In March 1989, a storm drove currents into the ground and into every long, grounded conductor sitting on it. In a transmission network, those currents push transformer cores towards saturation. The waveform distorts, protective equipment starts disconnecting things to save them, and the disconnections cascade. The entire Quebec grid collapsed in 90 seconds. 6 million people lost heating in March, most of them before they'd woken up. Well to the south, on the same night, a generator step-up transformer at a nuclear plant in New Jersey cooked its own windings and had to be replaced. Storms reach into orbit, too. In February 2022, a storm rated as minor heated the upper atmosphere enough to thicken it measurably at the altitude where a batch of freshly launched satellites was still climbing. Drag went up by half. 38 of the 49 never made it to their operational orbit. They came back down and burned. And that brings up 1859. That year, a storm hit hard enough that telegraph lines carried traffic with their batteries physically disconnected, powered by the current the sky was inducing in the wires. Estimates of what a comparable event would do to a fully electrified civilization come from insurance modeling and National Academy studies, and they run from hundreds of billions of dollars to several trillion, with recovery times from weeks to years. Those figures deserve a health warning. They're scenario models with enormous spreads built on assumptions about how many of the largest transformers would actually be destroyed rather than merely tripped, and specialists disagree sharply about that. Everyone agrees on the bottleneck. Extra high-voltage transformers are built to order by a handful of factories. They ship by specialized rail car, and the lead time is measured in months to years. Below all of that sits the low-grade permanent cost of a field that won't hold still. Polar flights get pushed south when radio propagation fails at high latitudes because those routes depend on high-frequency radio and there's nothing else up there. Airports close runways to repaint the numbers on them because a runway is named for its magnetic heading and the heading has drifted past the rounding point. Wells are steered underground by magnetometer. A degree and a half of error in the assumed declination walks the drill bit tens of meters sideways over a long horizontal run, which is the difference between hitting the target and hitting the well next door. None of that, though, is the question people actually ask. The question is whether a reversal kills us, and the honest answer is that the record says no. Reversals arrive every few 100,000 years. Mass extinctions arrive every 100 million or so. Line the two up, and there's no correspondence at all. The Geological Survey position, stated flatly, is that no correlation exists. Our own species has been through at least one collapse of the field, and nothing in the record marks the passage. A paper in 2021 argued otherwise, and it's worth knowing what happened to it. Using a preserved kauri tree from a New Zealand bog whose rings spanned the whole episode, the authors anchored a precise chronology. Then they claimed that the field, minimum 42,000 years ago, triggered a global environmental crisis, Neanderthal extinction, Australian megafauna collapse, the sudden appearance of figurative cave art. It got enormous coverage. It also drew formal published rebuttals within months from anthropologists and archaeologists. The objections were specific. The events don't cluster at that date. Recalibrated Neanderthal dates run well past it, and the cave art and ochre handprints appear in Borneo and Sulawesi thousands of years earlier. The chronology work is solid. The crisis is a contested claim, not a finding. The defensible part is thinner and more boring. Atmospheric chemistry models run with the field at 1/10 of its present strength give meaningful ozone loss at high latitudes, and surface ultraviolet increases several times larger than what the ozone hole produced. That's model output rather than measurement, and it should be said that way. But it's the physical effect with the clearest chain of reasoning behind it. For animals that navigate by the field, the disruption is stranger than people assume. A migratory robin's compass doesn't read north and south the way yours does. It reads the tilt of the field lines relative to gravity, and it can't tell one pole from the other, flip the polarity, and the bird carries on unbothered, because polarity was never the input. It does need intensity inside a narrow band. With the strength outside that band, the sense doesn't invert, it stops returning a reading. And here I have to walk something back, because I told you earlier that this field is what stands between the planet and the air you breathe. And that's the version in every textbook, including the ones I learned it from. The actual measured rate at which planets lose gas to space doesn't cooperate. Earth, Mars, and Venus are all shedding ions into space at rates in the same range, roughly 0.5 kilogram to 2 kilograms a second, and only one of the three has a global magnetic field. Modeling suggests why. A magnetized planet gets a magnetosphere, and a magnetosphere has openings over the poles where the field lines run straight out into interplanetary space. Close one escape route and you open another. Magnetization turns out not to be sufficient protection, and for a planet with an atmosphere as thick as ours, it may not matter much either way. The air itself is doing most of the shielding. Mars still lost everything, and Mars still carries the fossil of it. Those crustal rocks, magnetized once and never again, lie in bands across the southern highlands, hundreds of kilometers long, alternating in direction.
We only have that map because a spacecraft arrived with a damaged solar panel, which forced a gentler, longer approach at lower altitude than planned, which put the magnetometer far closer to the ground than the mission design allowed. The bands are absent under the giant impact basins, which dates the dynamo's death to about 4 billion years ago. The atmosphere thinned afterward. Whether one caused the other in the way everyone recites is exactly what's now under argument. So, is it happening here? A study in 2018 modeled the field in detail across the two most recent excursions and compared their evolution with the present. Neither resembles what the field is doing now. More usefully, the same model found earlier epochs when the field carried a weak patch, structurally very like today's anomaly, and both times it recovered without becoming anything. And there's the record itself. The field has been weakening by about 1/20th of its strength every century, which sounds alarming until you notice where the measurements start. Absolute intensity has only been recorded since those first observatories in the 1840s, and reconstructions from archaeological materials show that the dipole 2,000 years ago was substantially stronger than it is today, well above its own long-term average. The decline is real, and it's measured. It's a decline from an unusual high, heading toward ordinary. None of which is a promise. The dipole is still falling. The anomaly is still growing and still splitting. The pole is doing something no one has seen it do. If the present decline simply continues for another 1,000 years or more, the picture changes, and nobody can rule that out, because the honest forecasting horizon for this field is about a decade. That's the real state of it. The core is a machine we can only ever infer, running on a power supply we can't fully account for. It's monitored continuously from orbit and readable backward for billions of years in stone, and it can still surprise every model we have with a single, unexplained change of speed. Iron forgets, and the field is here anyway, which is why it can fail and why it comes back.
If you got something out of this, a like and a subscribe genuinely help.